Okie doke, in this video we're going to look at magnetic fields and electric fields combinations and looking at relationships between circular motion and the F equals BQV with particles in a charged particles in a magnetic field. So first of all, here's our magnetic field. As before in the previous video, and a positive particle. And that positive particle, when entering into this field, is going to do a nice circle. Normally I draw this a bit further down, but it doesn't matter. And obviously what we get as a result of that is the force acting inwards at all times, and that is circular motion. It's moving in a circle, forces at right angles to the motion at every point in time. That's Fleming's left-hand rule in action. So we have force is equal to mv squared over r. And that force is also equal to BQV from the previous video, where B is the magnetic flux density, these little green arrows, Q is the charge, V is the velocity of this particle that's moving in this magnetic field. In this equation, obviously, it's just a little bit of a throwback to the circular motion. So R is the radius of the circle, and V, velocity, same velocity, and the mass of the particle there. Now, there's some really interesting relationships we can draw from this here, because we know that these two forces must be equal to each other. So we can say that mv squared over r is going to be equal to BQV. And hopefully you can see pretty much straight away I can get rid of a set of v's and end up with a new term, which is mv over r equals BQ. Now, I'm going to spend a little bit of time with this equation on the next sheet because there are some very, very interesting relationships that we can draw from this to explain what's going on here. So the relationship was mv over r is equal to BQ. Now, mv over r is equal to BQ is a fairly relationship, isn't it? But we can also go mv is equal to BQR. Well, mv equals BQR is the momentum. That's momentum. mv is momentum. Very useful equation, that one. So we can work out the momentum of a particle by calculating the charge times the radius of the circle it's moving in times the magnetic flux density, and you can work out the momentum, and vice versa. Very useful. Another one is we can then break apart this V to be, because it's in circular motion, is 2 pi r over t equals V. So 2 pi r over t equals V. So let's put that in there. 2 pi r over t equals BQR. Well, look at what we can do here. We can get rid of another term. And we end up with a relationship that is m2 pi over t equals BQ. Now, this is very, very interesting indeed. This is a very interesting equation that we've just come up with here, because let's just rearrange this real quick to show you the very interesting version of this, which is t is equal to m2 pi over BQ. Now, this is absolutely fascinating because you'll notice there is no r term in here. This is the time. So the time it takes to go in a full circle is independent of the radius. It's completely independent. The radius has absolutely no effect on how fast it takes to get round the circle, which basically means there's got to be something else that always changes when the radius changes to make sure that this time always stays the same. If we've got a magnetic flux density and a particle of mass and it has that charge, well, the interesting thing is that mass and charge for certain particles, they never change. Those are never going to change. You're not going to get an electron that doesn't have a specific charge and a specific mass. Well, obviously, for all intents and purposes, that can happen. But for in this case and at this level, these aren't going to change. And so the only thing that can affect the time it takes to get round a circle is the magnetic flux density. That's the only thing. So I have a charged particle and I want to affect how fast it goes round a circle. It's going to be controlled by the magnetic flux density. That means that if I have a particle traveling at that radius and that radius, it will always get down around in the same time. If I have a particle traveling at that radius, it's going to get round in the same time. Always. Doesn't matter. As long as it's the same particle, it will always move in a circle that takes exactly the same amount of time. Fascinating, I know. So let's have a look at some other things to do with electric and magnetic fields, because it doesn't stop there. And we'll come back to this kind of relationship in lesson. We'll have a little chat about it then as well. So this is kind of part 2 to this video, really. We're just trying to finish off all the magnetic and electric field stuff. And this actually bit is very interesting because we're going to combine now electric fields and magnetic fields. So here's my electric field. I've got a positive plate, negative plate, and so any negative particle is going to be attracted there, and any positive particle is going to be attracted there and repelled, etc., etc. And what we're going to then do is we're going to add a magnetic field. So here's my magnetic field going into the page. And my positive particle, yet again, going to be moving into this field. There's my positive particle. So what are we going to see in this situation? Well, the positive particle, due to the electric field, is going to have a force exerted on it that's downwards. That force is equal to EQ, as you've seen in previous videos. That's electric field force. So the force due to the magnetic field is going to be upwards initially, as soon as it enters this field. Obviously, it's going to try to do circular motion, but when it's traveling in this direction, the force is upwards. So the force due to the magnetic field as it enters is going to be BQV. Well, what's really interesting about this relationship is used to create a velocity selection mechanism. So we can select the velocities of particles that are emitted. So you might have a number of different particles that are moving at different velocities through here, and we want to make sure we get the correct velocity coming out the other side for whatever reason. Now, we want to make sure it comes out there straight, and every other particle is deviated off, and because we don't want them. So we need to make sure that the right velocity comes out this side. So let's set these two equations as equal to each other. So EQ is equal to BQV. Well, quite nicely, we can get rid of the Q's. That means E is equal to BV. Therefore, V is equal to E over B. Now that is absolutely useful because we have a value of V that, say I want a specific velocity of particle coming out this side. I know that the ratio of the field E to field B has to be equal to the value of V I want. And so really nicely, I can work out what my electric field strength needs to be and my magnetic field strength needs to be in order to get out a specific velocity. And we call this a velocity selector. And you can look up how velocity selectors are used in your own time, but they're used for a number of different circumstances in industry and research, etc., and you can go have a look at those. But we'll kind of cotton on to these relationships in lesson, and we'll talk about them, and we'll put a few into practice as well.